streaming, right? All right. So let's start with the smaller fish.
Before you start with one thing, can you identify the areas that you are going to eventually optimize?
With this function?
Yes, just in general terms.
Pretty much the entire function.
Well, I assumed that, but
yeah.
What are the main components of that optimization? Are you going to find a way to optimize the projectile?
Yes. So we're gonna change the projectile at some point. At FAF we introduced a dummy projectile that really is a dummy projectile. We're gonna use that one. That prevents the uncreation code that we're seeing right here.
Yep.
That's one step. It also prevents, the projectile is a pretty big class.
Yes,
prevents all of that too.
All the baggage.
Yep. Then we're going to look into how we can get rid of these tables in tables, where we do all these type of looping instructions, and we're just going to apply a basic theory to allow us to find the 2 points that we're looking for, right? Because we're just interested in 2 points. So this bit here is going to get revamped quite a bit.
And the function that supports it as well, I'm sure.
These functions?
Get closest vector.
That one's not going to be part of the solution.
No, of course not. No, it's really just a table sort. And
yeah. And after that, we're going to look into all these vector calls that we have here. Those are all needless. They're all not required. While at the same time, they do introduce another table. So we're going to look into how we can cache that. And then last but not least, we have some alternatives for some of these engine calls. For example, in FAF, we have, if we go to unit.lua, and we go to onKilled, then we've got this self.dat is true value. And with that, we can prevent engine calls like these, continuously checking. And that initially seems like a small change, but I've benchmarked this.
The dot dead?
Yeah, in comparison to this engine call of being destroyed.
It's the only downside I ever found to it is that tiny bit of period between on killed and whatever death event occurs before dead is actually set.
True, but the C object is always deallocated after the onKilled function. Yep. So it could be that it takes one. It could be that there's a slide, it takes.
There's some there could be some overlap under certain circumstances.
Yeah. But that's not going to cause a crash. But just to give an idea, if we would do 1 million, this is 1 million. Yeah, if we do 1 million of these calls, then it would take 150 milliseconds to do 1 million of these being destroyed engine calls. But if we have a cached value, like here, then it would take about 9 milliseconds.
There's no comparison.
Yeah. And given that this loop is being run continuously throughout the game, right? If you have 5 or 6 UEF players, then this loop is going to get run a lot of times. You want the condition to be as cheap as possible. So that's the focus areas that we're going to tackle. And then you're going to have, at the very last, the upvaluing of some of these functions. Which is about 10% improvement, but if we would have a 10% improvement over the entire sim at some point, then that's always
noticeable.
That would be noticeable. Yeah. So that's roughly the idea, and we're going to after each break or during each break, we're going to compare what we have in the original code, right? So we've got the bytecode, and we're going to see this change into assembly calls or bytecode calls that are cheaper than what we had before, or just in general less than we had before. And that's going to give us the intuition of, are we actually improving the situation and given what we know of Lua from papers and from the Lua book and from benchmarks, we can confirm to ourselves that yes, we are improving the situation. So that's roughly the idea of what we're going to do. Does that answer it, Sparto?
Yeah, no, I wasn't. It wasn't really a question. I just wanted to know, what focus you were going to take on your improvements. Thank you very much.
All right. So let's start with the low-hanging fruit. All right. So I'm not sure if it's on this branch yet. Let me check real quick. Yes. So in FAF, we cache the blueprint in the unit right here, which means that if we have a call like this one, we can just change that to .blueprint. And that's where you can get the blueprint value from. This is again a similar situation where we skip an engine call and replace it with a value lookup, which we just saw is quite nice. We've got this bolt beam EMT blueprint, which is being used here. Instead of storing that in a local, we can just use the load K instruction, which is what we're doing right here. That means we can skip this local. So we're just inlining it, quite literally. If we're looking here, we're doing a get position. This returns a table. And what unpack does is it takes the table and returns them as separate arguments. So we've got a table and we return them as separate arguments as x, y, and z. But we already have a function that does this for us, which is called get position x, y, z. So we're essentially preventing this hidden table that get position was created, and we're preventing the unpack call. We adjust the y value here. I forgot why we did that. Let me check that real quick. Where is this y value being used? I think it's an offset.
It is. It's just an offset. Depends on what's being built, right?
Yeah, just an offset. Alright, so this is fine. These are just some lookups. Let me check real quick because we cached these values in unit. Yep, but we didn't cache the offsets. Nope. So this is fine. Then we create this projectile. Now by all means, we're gonna go back to this. But for now, we're just gonna forget the fact that the projectile is doing a lot more than we think it's doing. And we're gonna skip this line right here. So we've got this if statement. If we have build effect bones, I don't know a situation where we would not have those.
Sometimes drones.
Yeah, but the drones have beams too, right? They have the. I think they have this too. Maybe modded units.
They may not define it in the BP.
Oh, like that. Alright, fair enough. So there can be situations where we don't have them. And then we just create a bunch of beam effects. This is a local that we set to nil, but we don't use it anywhere here. So we can just get rid of that. Then if we look at this for loop right here, we've got the build effect bones that is running over. Now the build effects, just to make sure that we understand what we're working with, let's just do a quick log wrap build effect bones. It never hurts to look at what we have, because Lua is not strongly typed. And that means that just like in JavaScript or in Python, you don't know the type while you're working on your program. But during runtime, you can find the type. But in this case, what logwrap does is it unpacks the value and it puts it into the console. So let's make a new engineer. Let's see what you get. Right, so these are the bytecodes again. And let's start a build. And there we have it. So
Yes.
we've got a trash bag. And we've got this turret muzzle. And if we look at the bone names, then you can see that we have a turret muzzle right there too. It's a bit hard to see. Let me see if I can fix that. Here we go. There's a turret muzzle right there too, and that's the bone that we're referring to. And you can see that the build beam is coming from that bone. So if you would have, for example, the bigger engineer, and we would do the same thing, then now you can see we have 3 turret muzzles, and that's the 3 here at the top of the build arm. So what we're dealing with here is not magic by any means. Let me check real quick. Ah, bone 0. Alright. So that's the information we have. And this is a trash bag. And trash bag is just defined in Lua. And the idea of the trash bag, for anyone that has ever done any memory management, the idea of this is to make sure that any value that has to be destroyed at some point gets destroyed. So that memory is cleared. So we've got a trash bag, table of bones, unit being built, unit that is building. Alright, and for the sake of my computer, I'm gonna toggle those off. Alright, so let's look at this. We've got this add function right here, and we've got it here too, and that is part of the trash bag, which is this add function right here. Now what we can do, what happens here with this add, let me see if I can find it in the bytecode. There should be a self, that's right, this one here. So what happens when we do this colon instead of a dot, we could have written it like this, dot add, and then this becomes the first argument. This is doing exactly the same thing. So this colon is syntactic sugar, which is a fancy word for saying I want to write it shorter. That ensures that the object that we're calling it from becomes the first argument, which is in this case between quotation marks self. Right? That's a pattern that we see all over the place. For example, if we look at the projectile, first argument is self, 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 and that means that we expect people to use this colon and then immediately automatically append ourselves as the first argument. But sadly, there is a small overhead when you use this. So we could instead write it like this. We can get the functions directly from the class, like we're doing here. And instead of doing this table operation here, we can just directly reference the function like that. And then we prevented that table operation that's part of the self operation. We could do the same thing here. So we move this fella inside, and that fella inside. And then we've got this trash add. Oops. Hold on. Press it one too many times. There we go. Then we've got an access pattern question here, but I think I already upvalued this one. Yeah, it's right there. So typically when we get a function that is not defined in this file, so this function create attached emitter does not have its definition set in this file. It means we're getting something from the global table. And what does that look like? Well, in the code it literally says get global. And what get global does is it rewrites what we have here into _g dot, which again is a table lookup right there. So again, that's some form of syntactic sugar. We can prevent this by making this function address part of the closure of the function that we're working in. And we can do that by simply saying local is, whoops. Alright, this is what happens when your laptop is running at 5 FPS. Local is that. So what happens now is that we've got the global version here. We cache it into a local scoped version. And when this function keyword is made, a closure is created, and a closure essentially captures everything that this function can reach, and this local becomes part of that closure. And that is called an up value. And an up value is significantly faster to access than a global is, because instead of secretly adding this g dot, we still have a direct reference to the function itself. And that's why this is faster. So now this is an up value instead of a global.
That's the same kind of improvement that you used on the trash bag. You're just eliminating that lookup in front of it.
Yeah. But the difference is that if you look at the instructions, that the one is a global,
one's a global, yeah,
and the other is a self call, and then a function call right there. But it's very similar, yes.
Yeah, a lot of the optimizations that you're going to end up doing if you do this work are going to be around that very same idea, minimizing the number of lookups, whether they're lookups to global tables or lookups to functions within a class or things like that. It's all about shortcutting those steps. Where you can.
Yeah. That's indeed the idea, especially for example the global table, because that's a very, very large table, and that means that it's got a very large chunk of memory used, and the chance that that entire table is in the L1 cache, which is the fastest cache, is pretty low. So the chance that you need to dig deeper into the memory of your computer, quite literally a haystack, is pretty big, and that makes the access pattern a lot slower. And with this, again, because now it's an up value, because it's part of the closure of the function, we prevent that table access, and we just have access to the
you're looking directly at the function itself, and not looking for it first.
If we did end up removing the check for build bones, would that improve anything notably?
I'd say in this case probably not. I don't think we're going to notice it, because it's just one instruction.
And you would assume that the build effect bones, all the work to get the build effect bones was done before you got passed over to this function anyway. Yeah,
exactly. So all the difficult work between quotation marks is already done at this point, and we're just checking if that actually paid off. So I don't think it would matter in this case. That's why I'm also leaving it in here. There's probably a good reason why someone put it in there at some point. Alright, so let's look a bit deeper into this function. So we've got this going right here for us, with the exception of this one. So let's add a to-do. And another exception is this one. So we add a to-do for that one as well. Let's dive a bit deeper though, because we've got these table lookups right here to determine the mesh extents of our of the unit that we're building. And the mesh extents is essentially, if you take the model itself, alright, so let's make this a good comparison. You've got the skirt, which is the outer green line of every structure that we're looking at right now. That is used to determine, can I be built here? And we've got the mesh extents that essentially literally determines like a cube box, like a cube surrounding the mesh, to help us determine how big the mesh really is. In this case, we use that to scale the effect. Those mesh extents are stored in the blueprint table. Now we already retrieved that one, so that's nice. But in this case, we already cached this value right here, which means that we can prevent all these lookups that we're doing here, these two table lookups, by saying unit being built, and we change it into 1. And same here. Now this value is always set, so we can remove these. And I think the mesh extends Y.
Not all mods will set that value.
No, that's true. But this, the fallback is using the footprint size. And that's what we were having here too, right? So this is the footprint size, but it multiplies it with a slight multiplier. We're just going to forget that we did that. So let's just get rid of that. If this causes any errors, then we'll find out later on. So that's a bit simplified right now. We multiply this slightly. I'm not entirely sure why we do this yet. Oh, right, no, that makes sense. So the build mesh extents is essentially a rectangle ranging from this corner to that corner. But what we're interested in this next section is the information of retrieving those corners depending on the position of the factory. And the position of the factory is in the center, right? That's what we extracted right here. So if we would look at our little drawing that we have here, then this bit here in the center would be X, Y, Z that we retrieved. Alright, my computer is definitely not liking what I'm doing. Right, that would be this center point here. I'm gonna make it red for the sake of it. And I click too many times because I'm impatient. There we go. Let's make that red. And then we put another point in the center. Oh, my computer is not enjoying this. Alright, there we go. We've got a point. Then we have the mesh extent itself, which is this right here. So that would be the mesh extent 6. Right, that's that one right there. And then we have the OX value, which is what we're having right here. And that is this distance right there. Let me actually make that a separate line. And I'm gonna make that purple. That is this bit right here. So this is OX. There we go. So this is just to visualize the data, the information that we're having. So that's the OX in the OZ value. OZ is the same thing. Typically, we live in the XY plane when we look at graphs, but in Supreme Commander, the Y-axis is up and down, which means that the X-axis is left from right, and the Z is front and back, and the Y-axis is up and down. So that's why these are called OX and OZ and not OY, as some of you may expect. And then we've got the beam setup, right? We've got the beam from entity to entity, so that's the beam that we were looking at right here. We've got that one set up. We've got the attached emitter still. All of this is slightly faster with the exception of this fella right there. And now we're getting to the point where we're actually determining those two points that we're interested in, right? So that would be the, in this case, this corner here and the corner there. For the sake of it, I'm gonna skip this real quick, and I'm just gonna continue down here because there's a separate section in the next video. Alright, I should not open up programs because everything's crashing. And we're gonna go back to this in the next video. We're just gonna jump ahead and look at this bit here. So what's happening right here? Well, we already determined previously that this wait seconds is a Lua function, which is what we're looking at right here. It's got a bunch of globals, tables, multiplications, another call, another global, and a call, and it returns. Which means that for this operation here, where we wait 0.7 seconds, a lot is happening. And this function is defined in sim_init.lua. Here it is. And just as a small exercise between quotation marks, let's just compare what we have here. We've got line 25. We've got a get global. This get global is this math keyword right here. That's a global. We've got a get table, which is this dot right there in between. And what we're getting is the max operator. So we want the largest number, 1 or n times 10. We reload a constant, which is this 1, and it's this 10. We multiply that. Then we perform the call. So the call is actually the max function that we're seeing here. LT is less than, which is this check that we're seeing right here. We jump if it's true, and jump means we skip the code in here. You can see that we're jumping one instruction in that case. If we don't jump, then we add, right? So given what we have, we add 1 to ticks, and once we're done with that, we do another get global, which is this wait ticks, which is defined right there as a global. We move the argument that we made here as an argument. We perform the call, which is the call right here, and then we return, which is the fact that there's always a hidden return keyword in every function. So that's what we're looking at right here. That's what this bytecode is telling us. But what does it tell us, right? As a programmer, what it tells us is that it's actually a very expensive way of saying, hey, you give me some seconds, I multiply it times 10, I make sure it's larger than 1, and then I call this coroutine.yield. So let's skip all of this and get rid of you, get rid of you, get rid of you. And we're going to here at the top, chances are I already did it. Yeah, here we have it, yield, coroutine.yield. So instead of saying wait seconds 0.7, we can just say yield 7, right? Because that's what we were doing. If we look back at that function right now, then we multiply it by 10, and if it's larger than 1, then we add 1. Okay, so we wait 8. There we go. For those that don't really understand what's going on here, the game has 10 ticks per second. So the simulation has 1/10 of a second per tick. And what we're doing with a yield is essentially saying, hey, I want you to wait until the current tick plus 8 or plus 7. Because if you do a yield 1, then you're saying, I want you to wait until the end of this tick. I want you to wait until the end of the next tick, etc. And now you're saying, I want you to wait until the end of the 7th tick. And that's why we're saying yield 8 here, because originally this was wait seconds 0.7, right? So that's 0.7 ticks down the line. So now we essentially skipped all of this logic and just did a call and a load k, probably, but we'll check afterwards. And we've got more happening here. So we've got this warp, which we didn't upvalue last time. So let's do that, right? This warp right here is a global by all means, because it's not defined in this file. So let's just say local warp is warp, and now we get the same closure idea that we were describing before with the create attached emitter. So now we have a direct access to the function. We have a vector here, and vectors are a bit more nasty because vectors, what they do essentially is they say, well, we've got this local v is a table, v1 is this, v2 is right here, v3 is right there, and then by all means, if we were in the function vector, we would return it, and it does a set meta table v vector meta. And what this means is that we're introducing additional functionality to this table, and all the functionality that we're adding is that we can say, well, instead of saying v1, we can say v.x, and instead of saying v2, we can say v.y, and instead of saying v3, we can say v.z. That's all this meta table is doing. It's not doing anything else. But what's more important is that we are allocating a table here. We populate the table. We set a meta table. And then we use it in this warp function, right? It was like this. And then we forget about the table, which means that we did a heap allocation. We extended the table twice. So the table starts with 0 entries. At this point, it has to retable because we're trying to add something to, we're trying to add one element when we can only occupy 0. So we increase the size to 1. We have to retable because we're trying to add an entry. Well, we only can sustain 1 entry and we already have 1 entry, right? So we have to expand ourselves to 2 entries. And then we have to retable, again, same story. Our table has a size of 2 and we have 2 elements in it. We're adding a third one, so now it's being increased to 4. And essentially we go from 0 to 1, 1 to 2, and then 2 to 4. So if you would have a 4th here for some reason, because we're working with quaternions, then this retable operation would not happen. But regardless, what this really means is that we allocated a table on the heap, we allocated a table on the heap, we allocated a table on the heap. And if this sounds very redundant to you, then it is. So we can do better, right? So what did we do last time? Well, last time we noticed this behavior too, and instead of allocating a new table, we essentially say, well, we're just going to reuse the table, and we're going to do these steps, and we're going to do, everything else we're going to skip, and that's what we're going to do too. So we've got this vector cached here. Let's add that here at the top. Vector cached. And instead of creating this new table by doing this vector call, we're just going to reuse this table. So now we can effectively skip all of this. These comments no longer apply. Why? Because we're reusing the elements that are at these that are already allocated at some previous point, right? So we're just reusing the same memory address here, which means that there's no retable happening because we're not increasing the size of the table, we're overriding the table, or elements of the table. So let's get rid of these.
Can I interject one comment there?
Yes.
The nature of table allocation, as Jip has explained there, applies to any kind of dynamic table growth.
Yeah.
So if you are inserting new entries into a dynamic table, the same thing can happen. And if you go back up and look at Jip's reference to where he creates vector table, you'll see that he saves all of that, the reallocation work, by declaring the table to have 3 elements at the start. Yeah. That causes that table to be created immediately with one table allocation of 4 elements. Even though you're only specifying 3, it will actually create a 4th element there.
This.
Yep. Yep.
In that case.
And anytime you're doing any kind of table manipulation that's dynamic like this, where you want to have, growing entities, try and think ahead to where you can specify your table size in advance. It will save a lot of effort, not only for the garbage collector but also for your CPU.
Yeah. And for those wondering, are you serious? Yes, because in this sample paragraph on Lua performance tips, they describe this exact behavior in reuse, and recycle.
Yes.
Which is right here. They describe the exact same phenomena. Which sounds silly initially, but it's the only choice you can make. Right? Because if you say, well, my table starts with 10 elements, then if you only have a table that uses 2, you're essentially wasting 5 times the amount of memory. So what's happening here is that we're making a trade-off between performance and memory usage. And considering that Lua is with its garbage collector quite expensive with its memory, they chose for the reduced memory usage in this case. Yeah, but this was a vector in this case. Although I don't think it matters in practice.
No, it could have just been a plain table with 3 elements, and it doesn't even have to be a vector unless you want to use the X-access methodology.
Yeah. Which the engine doesn't, but some Lua code does, so that's brilliant. Yes. So there's really no actual need for that vector table, except for the fact that we thought it was great to do that. But that's what we're doing here. So it looks like a small change, but internally it's a pretty big change, right? What we did here, we skipped an entire function call with all the logic a part of that function. We skipped this function that returns a new table that we're just going to throw away again because we're not storing it. And we were reusing the same table here throughout the entire function, which is very good for your cache. So all of that's great. And I'm going to add a to-do here up value for later, because we can cache this function right here too. Alright, now what we're seeing here is roughly the same thing that we were seeing here, right? We've got the warp right there. It's getting a fraction, and we can just change this up again. But before we do that, let's save and check if we didn't break anything, just to make sure. Boink. No, seems to be fine. All right. So
last words.
Yeah. So let's do this again. Right, we've got this little fella here. We've got cx1 and the x. We've got this whole bit right here, and we've got this one on the, and we prevent a table allocation just like that. And then we do the same thing on this end, but here we have cx2, 2, cy2, and that appears to be the same. So we can get rid of this. And here we have another to do up value, which we're going to do in a bit, and to do up value. And then here at the end we have a wait seconds again. We just went over that, so we're just gonna copy this. We multiply it by 10, which is 5. We add 1, so this is 6. And for those just jumping in, that logic is from what wait seconds does, right? Times 10 plus 1. We've got a to do up value, to do up value, and the condition itself. So in FAF we have this onKilled self.that is true, and in case onKilled gets skipped and we go straight to onDestroy, we've got self as that is true here too. So instead of checking if the C entity is destroyed, because that's what this is checking, we can just check if from the lure perspective we consider the unit to be dead. And if that's the case, then we're fine. So we just removed 2 engine calls right here, and we can do even better because there's a not and a not, but we can also write or, and now we skipped one not operator. Right? If this is that, actually this is not even required. Wait, it is. Sorry. So if one of these are true, then the while loop stops and the body is no longer triggered. So let's see if what we're doing here didn't break anything yet, because I'm still waiting for that moment. Yeah, seems to be fine to me. My game's a bit laggy, but there's no errors either, so that's good. Alright, and this is the easy bits that we did. I'm gonna pause the video again, and then we're gonna look at one of the more difficult optimizations, which is this section right here. Yeah, and then after that we're gonna finalize everything, do all these to-dos, because that requires a bit more explaining, and we're going to switch out the projectile for one that doesn't create so much garbage. And then we're pretty much done with this function. So let's pause the recorder again, unless people have questions right now. I see I got a message from someone. Oh, that's the AI chat.